But Sven Hilbert, if you Google me, you'll find me on at the University of Regensburg, and the slides should be up there. The talk is called "Too Fit is to Overfit," as you know. It's the first one in line because, yeah. So anyway, I decided to provocatively state that these are the 3 goals for an empirical science and relate them to different kinds of statistics. So descriptive statistics, we have them already because obviously you all know them. What you do is you will have plenty of data and you'll just build summary statistics to make them more easily understandable. Kind of the talk we heard yesterday, you just rearrange them and maybe you just get the gist out of them to get the information that you need. For example, in summary statistics, because obviously if you ask a lot of people who they vote for, you're not interested in every single vote of every single person, but in frequencies, right? So then you get the second part, the explanation part, which is what inference statistics is. That's all right. I get that all the time in lectures. So inference statistics is what, well, is the field that is mostly concerned with the explanation a lot. I mean, they talk a lot about prediction too, but well, I guess it's explanation for the main part. And obviously they're built on plenty of assumptions. You got p-values, and then you assume that if your assumptions, well, you state that your assumptions are true, you get to do statistical inference, which is really elegant and really cool. And then there's a third part of an empirical science that I think is very important, is the prediction part. And the prediction part is what predictive modeling is focused with. And just to clarify, because I've heard a lot that I might talk about machine learning today, which is not exactly true. I mean, I'm going to talk about predictive modeling, which is basically a philosophical concept that is a big part of machine learning, but machine learning is so big and it's really hard to differentiate between like machine learning. Actually, machine learning uses statistics. So what I'm going to be talking about is basically predictive modeling and what the philosophical idea of it is. And this is the part that is concerned, obviously, with prediction. So predictive modeling uses techniques that focus on the prediction of novel data, which is something that I think is, well, actually caused a lot of confusion because we talk about prediction when we do inference statistics a lot without actually predicting anything, but we'll get to that. So now, if we have these 3 areas, I think the description part is pretty easy, right? I mean, this is descriptive statistics, and I don't think anyone wants to argue about that one. So I'll focus on explanation and prediction. And again, when we talk about explanation, we usually talk about a culture of statistical inference that is treating some data generating process, or we say sometimes the ground truth function, as known. For example, can you see that? Yeah, you can see that part. If I, for example, have my x here, my y here, and then I plot like this, and I got plenty of data, right? So I do that a lot in my lectures, and I ask the students, like, what do you think the relationship is? And they all say, well, of course, it's a line, right? It's a linear relationship, which is easy to see and it's good. And if that is the case, well, because you're a human being, you're used to using statistics, you can't see that. And I could see that. I could, like, I mean, artistically, I'm not great, but the line's more or less central. And I guess most of you would have drawn exactly the same line. So this is what we see, and this is how we get our assumption. If we do use those assumptions, we can draw inferences from these assumptions and from the data. And we do have some assumptions, right? We'll say, all right, let's say this variable bool follows a normal distribution, finite variance, and, well, I don't know, let's say let's do some mu here. And so we got that, right? That means we have normal distributions and we use those. The errors are usually normally distributed with the mean of 0. And if all of this is true, then we can start doing statistical inference. Okay, so that is one idea. You have a data generating process, which in our case is this one, and we assume that we know it, and so we can infer from it. And then there's the second culture. I don't know, some of you might realize I'm kind of just citing Bryman, the 2001 article, The Two Cultures of Statistical Modeling. And the second one follows the idea of treating this data generating process as unknown. So saying that, well, I don't have any idea. It might be linear, might be exponential, might be a polynomial to some degree that I can't even think of. Maybe I don't even use some kind of a linear predictive function that I then generalize. I just use some kind of a regression tree or whatever I want to use. I'm going to get into that later. And so you say, I don't have any idea about this data generating process, right? It's just not here. I just have some data. And what I'm going to do here is I'll just see which model fits my data best. The terms I'm also going to use, and actually, thanks a lot, Jan. Yesterday I read this article because I told him what I was going to talk about, and he told me that this Homo heuristicus article could be very interesting to me. So I scanned through it and I saw there's actually a lot of those ideas that I'm going to present here are going to be part of it. Well, they were part of the article, so that was really cool. And I think in this one, well, because I guess some of you might know it, they explained the concept of bias and variance very well. But for now, let's just say if you have a model that has strong assumptions, you would probably say it's pretty biased. So because there's a strong bias, the model can be fitted to the data, but only based on those restrictions that the model has. So if I fit a straight line down here, well, I'll probably just get the mean or something. So something with a slope of 0. Right, same goes for U-shaped curves and whatever. And on the other hand, if I fit something very flexible, well, I could probably just model that. So in general, it seems like a good idea to be a little more flexible, but we run into problems if we do that. And well, I had some nice examples on my slides, but I'll just do it in a more theoretical way. You run into problems because what happens a lot is that you overfit to the data. I mean, we always say that in general, you get a value because, well, I mean, that's like classical testing theory, right? You get the true value and you get an error. And also, like, as you see here, you have the data generating process, and whatever your data are, they are usually, well, hopefully kind of related to the data generating process, and then you get some kind of residual. And if you fit your model perfectly to the data you get, you fit it to the truth, the ground truth function, or the part that's caused by the data generating process, and you also fit it to the error. If you do that, then your model will obviously not exactly represent the ground truth function. So what's happening? Let's say I don't have different colors, right? So, well, I'll just try doing this again. This is my function. And then I get like a very small sample. Let's say I have 1, 2, 3, and 4, just 4 sample points. So, and then I can either do that, use a very biased model, which would also give me like a horizontal line and it wouldn't do much good. Or what I could also do is I could use a very flexible model and just fit it like this. Might look a little better, but I said I'm going to talk about prediction. And if I use the term prediction in the way it is used when people usually talk about the regression or linear regressions or regression models in general. They say, oh, I can predict this and this, well, these variables by using these variables to a certain degree, and I have an R squared that is, I don't know, 0.4 or whatever, and this is how well I predict the data. But this is not really prediction, right? It's actually post-prediction. You say something after you've measured it. So it's like you see an apple fall from a tree and you be like, okay, that apple just fell from a tree. That is nice. You might have a nice explanation for it, right? Like you get gravitation, but if you use it right, if you explain it right, then you can maybe fly to the moon someday. But in general, what you would do is you want to predict. So you want to try out and see if you can predict novel data. And you want to see that is what you long for usually. And if you use a very flexible model, then obviously you model the error as well. So if then you get novel data and it's caused by the same data generating process, this one here, but it's a little different, right? It could be here, and then this one is a little down there, and this one is here. The differences are going to be, well, the differences between, there it is. Oh, no, there it is. Between the predicted values and the actual values are going to be very, very big. And this is the problem with overfitting.
Can I make an announcement?
Yes, please.
Did you just start, or are you in the middle, or are you almost done?
I'm kind of in the middle, I think. It's 50%. Okay. We can make a pause.
Okay. Sure. Sorry
you can go to the front.
Yes, you can go here. I think
everyone
will see you here.
Okay, sorry to everyone for the delay. According to our regulations, the janitors should have been in here at 8 o'clock, but no one was there. But the good news are the room is open now. We can move over, and okay, and when you prepared whatever you prepared with slides, I mean, that may be possible. If it will be possible over here, over there, I don't know if it's possible here.
Yeah. What I propose, he ends his presentation. I go to the room to prepare
things.
Maybe when he ends,
then we move over.
Back to
okay.
Room.
Yeah. So
who is the first person who has to present? You give me the presentation, please.
Yeah.
In the USB stick.
Yeah. I want to do it with my laptop. Joachim, der Leiter vom technischen Dienst kommt auch um 9:30 Uhr, um aufzuschließen. Mit dem haben wir telefoniert. Das ist dann doppelt genäht sozusagen. Das ist nicht nötig, aber
weißt du, wie der heißt, mit dem du telefoniert hast?
Rake.
Okay, ich kann nämlich eine Geschichte erzählen mit der Begegnung mit einem vom technischen Dienst. Die ist ein bisschen abenteuerlich.
Wir müssen noch abfragen, weil er auch nochmal kommt. Der weiß nichts von dem
ja.
zweiten Übergang.
Okay, kannst du dem nochmal...
Der ist unterwegs. 9:30 Uhr ist der dann.
Herr Bohle,
Ja.
Also machen wir es so.
Aber Sven macht jetzt noch deinen Vortrag zu Ende und das nächste Mal machen wir das so. Ja? Okay?
So I'll wait 1 second until everyone starts. Okay, just for everyone on Zoom, I think what we're going to do is I'm going to finish this here using talk, and in the meantime, we're going to prepare the other room so we can just switch to the other room afterwards and the other talks can start. All right, so I hope you can see some of it, and it's not too confusing, but I'll try to wrap it up in a way that, that kind of everyone can take away something from it. Anyway, so what I just explained was, okay, we do have a problem if we underfit, if we have a very biased model. We do have a problem if we overfit, if we have a very flexible model. And I said that what I think is very important is the prediction part, the actual prediction part, and I think that I've never said that, but I guess it was obvious that many assumptions that we have, if we use super biased models, are not going to hold. So basically, I say that it could be a good approach to be more flexible with your models. But as you can see here, what you have to do is you have to be very careful so you don't overfit to the data and model the residuals. Okay, and I said, well, what's happening here is that you probably get predictions that are very off. And a measure that I see many people report when they report predicting data is R squared, right? R squared is, we use that part. R squared equals 1 minus. Do I have a sponge or something?
Back there.
On the right, on the right.
Okay.
Let's see.
Oh. Yeah. Here we go. I'm sorry, like ever since I became a dad, I'm like, it's been harder for me to kind of maneuver through things, but oh well, I guess that's what happens. Anyway, so we got R squared here, and R squared, what does R squared tell us? R squared, what they tell you, what they told me when I was studying psychology was R squared is a part of the variance that is explained by the model. And that holds well if you use it for the sample you built your model on. And as I said, I don't think this is the right idea to evaluate your model using this data, except if all you want to talk about is the data you just had. If you want to talk about predictions that you make from novel data, well, you use it with novel data, right? So what if you calculate R squared for novel data? Well, R squared, what we do is we say, okay, we have some kind of predicted value by our model, right? Because our model works like our predicted value is, well, let's say we just use that. That's a little easier. That's my notation. So use that. So we got this, right? We predict y by x and by some parameters. So we got a predicted value, and we say, okay, this is the variance in y that is explained by the predicted value, and 1 minus is obviously the residual because it's just the value following the model is just the true value and the residual. So 1 minus is obviously the residual, and if you sum all of them up and square them, you get the square differences between the predicted values and the real values, and then you divide it by the variance, which cancels out, so it's not really the sum of squares actually. And you get your true y values minus. So that is your sum of squares. So you divide that. And if you are very far off, let's say you have some data like, well, you just have a random sample and you fit your model. And well, I did a simulation. Actually, if you download the slides, there is the link to a repository where I uploaded the simulation code. So you can, if you have R, just download it and run it, and then you'll see all the simulations. They simulate kind of exactly that. And you would be able to just to reproduce the figures that I have on the slides. And so let's say this is your sample and this is your line, and then you will predict, you want to predict novel data, and your novel data kind of, do circles here, is like this. And the mean of your novel data obviously is here. So your square differences are kind of small because your variance is not very high, but the difference between the predicted values and your true values, they are very large. So these square differences are bigger than those square differences. What happens? This one becomes larger than 1, so the whole term becomes negative. So what you get here is actually a negative R squared. And this is what you observe a lot if you do that. So your new model, if you want to interpret it in terms of, well, the variance explains negative variance, which is obviously not true because it's not used for the training sample. But what it means is you're a lot worse than just taking the mean, than just saying, okay, I take the mean value and this is my best guess. So no need, if you observe that, no need to estimate the regression. Just take the mean. That's your best guess. Take the median for most cases. So anyway, now this is what happens. How can you avoid that? Obviously, that's on my slate. Plenty of data. The more data you get, the more correct your model will be. So if you get a lot of data, the differences between novel data and well, your training data is not going to be so big. Also, as I said, I think for evaluating your model, a good idea would be to actually use novel data and not use a measure like R-square. You can do that. It tells you there's plenty of merit in it. There's plenty of merit in statistical inference, right? Don't get me wrong. I love the general linear model. Well, don't tell my wife I said that, but in general, it is something I really find elegant. But I think for a lot of use cases, or in a lot of ways that it is used, it's actually not the right approach. So, as I said, I think the prediction of novel data, adapting your model fit, which is, to wrap that up, usually a model that is not overly flexible, not overly biased, so mostly not a linear one, but not a, I don't know, super high degree polynomial, but something in between. And how you figure that out is you just repeatedly test it.
I have a question.
Yes.
Oftentimes you do not have new data.
Yes.
And an idea you could use then is cross-validation.
Yes, and this is how I wrap up my talk.
Oh,
this is exactly what I'm getting. Yes, what he just said is, if you don't have so much data, you could use cross-validation, which is a great idea, and this is exactly why I will continue with cross-validation.
Okay. Sorry for speaking.
No. You just made it easier for me to just switch over to the topic of cross-validation. So what I was going to say is, yes, if you do that, and you want to do it repeatedly, and this is something that they do in machine learning a lot, is they use resampling. In resampling techniques, there are plenty of them, but cross-validation is actually the one that they use most. And I have, 5-10 more minutes almost. So, okay, I can do that. So before I go into cross-validation, which will be the end of my talk, and which is also old news to a lot of people probably. So I just want to explain why it is so important in the field of machine learning. Because in machine learning, as I said in the beginning, predictive modeling, you use very flexible models a lot of times. We had random forests yesterday, and we do have boosting, which is also very flexible. Well, the thing is, if you have a very flexible model, like a tree, like a cart, like, categorization and regression tree, you split your sample like a mathematical tree, and just to make the nodes purer and purer and purer, you say, okay, I divide between men and women, then I divide between people that are older than 40 and younger than 40, and I do that. And as long as every person has a different pattern, you can just make a tree so big that you get so many branches that every single case is predicted individually. And this is like the most extreme case of overfitting, right? But you can do that easily. This is not a problem in many applications for many of the applications we had in psychology, because we use linear models and they never fit perfectly to the data. But if you use super flexible models like regression trees, recursive partitioning, random forests, and boosting, which also works with trees, but in a sequential way, you do have to actively avoid overfitting. And this is something that I think you will find over and over again when you think about human perception as well, because we do not overfit when we perceive the world, right? If I'm like a caveman and I find an apple and I eat it and I'm like, oh, that was good, I want another one. I'll never find an apple that looks exactly like the apple I just ate. So what I need is something that doesn't fit exactly. I can't just remember every single ray on my retina. No, what I need is like a canonical image or something, something that is abstract enough. And this is what we do. We need to be abstract with our models. We need to be in between being too simple, right? Because if not, I will just mistake like an apple for a rock or something, and I'll just lose all my teeth, and that'd be a bad idea, right? So, but at the same time, I need to be can't overfit. So I'll recognize another apple. And so you have to take active measures. If you do, for example, a random forest, I talked about that. Well, I asked a question about that yesterday. a random forest implements that, for example. Random forest is plenty of regression trees, or not regression, it could be categorization trees, but plenty of trees. And in order not to overfit, you say how deep they can grow, well, you know, how many splits. And also what they do is they use actual, uncertainty. They induce actively uncertainty by bootstrapping. They do, for example, they use the whole sample and they bootstrap 1,000 samples. So 1,000 trees, this is why it's called a forest, right? So you bootstrap 1,000 trees with different samples. So you get a little different result every single time. And then again, you induce randomness on another level. What you do is when you get p variables that you can choose from, you decide there's this hyperparameter that you set, which is m, and m usually is 1/3 of p. This is the default. This is why I asked about it yesterday, actually, when we had 3 Qs. And if you use the default value, you would probably just randomly select a variable for splitting. There'd be no active selecting of the best variable for split. So that might make the performance pretty bad. Anyway, so if you do that, you just actively select just 1/3 of your variables to not overfit. So you avoid that, because it has been shown plenty and plenty of times that the performance gets a lot better. And this is the concept. I thought, like, that when I first thought about it, I was so amazed, because I thought, wow, they actually try to not fit the data as well as they can. That is news to me, because I always thought if I get an R of 1, then I'm like, well, this is the best I can do, right? And obviously it's not. So, and then for boosting, which is sequential, they do something that is called early stopping. What they do is they use test samples, and as soon as they fit the model better and better, and as soon, and this is something that you observe when you do that, at a certain point, the fit to the test sample, the performance with the test sample gets worse. So you see if this is your fitting, like how well you fit, and this is your error for the test sample, like if the fit's bad, you get worse and worse, and then if the fit gets better, it gets worse. Yeah.
There are some criteria.
Yes.
VIC criteria.
Yes.
Like
Yes.
VIC
Yes.
So these are criteria like grades that you give to the different models that you have created on the road.
Yes.
And you pick those with the best grades.
Yes.
And go for them.
Yeah, information criteria. You can take those, but you mostly would use something that is a little different from them, because also they have parts. For example, they always information criteria always include the number of variables that you use, for example. And you could also use just very simple criteria like the MSE, like the mean squared error. You can use mean misclassification error for categorization, but it's exactly what you do. And these criteria, you could use the curve for that, they get worse. And this is what you have to look for if you want to generalize, if you want to predict new data. So now to wrap it up, what can you do? Because obviously you always have a problem with not having enough data. Well, you resample, you use your data, because as we saw yesterday, you can split your data, which is called a holdout. You just take a test sample and a training sample, also 1/3 and 2/3, usually 2/3 to train the model, 1/3 to test. But then you lose 1/3 of your data, right, to train the model. So what you usually do is you just use your whole sample. If this is your whole sample, and then you do a k-fold cross-validation. I'll just explain that for 3-fold. You use the sample and you divide it into 3 parts. And the first part, then you do 1 time. This here is the training sample, and this here is the test. And the second time, this one is the test, and these 2 are the training. And this time, this one is the test. And these 2 are the training. And if you have enough data, you can do that 10-fold, which you usually do. And do that, and then you just calculate your performance measure to estimate the generalization error, which usually, let's say, classification is the mean misclassification error. How many cases did you misclassify compared to the total number of cases, right? So you do that 3 times, and then you take the mean performance measure, and you can do that, and this is the beauty of it, or maybe it's also the danger of it. You can do that because you're not tied to p-values or any assumptions about distributions, because you don't need to say, okay, I can generalize because of my probability density distribution. No, I say I can generalize because I tested it and it worked. And so you can use plenty, as you saw yesterday, 8 different modeling approaches. And then when you do that, choose the one that performs best. Obviously it's biased because it performs best with your data, and you would need like more loops. This is called nested resampling, but that's too much for this talk. But in general, the idea can be use your sample, divide it, resample, try to predict the novel data, use that to evaluate your models, and well, you have an idea about the generalizability of whatever you find. So doing that, that's about it. I think that's my time. I hope that was okay, even though I didn't have any slides, but you can download.
You know that this topic is one of the topics that interests us most, the fast and frugal guys.
Oh, that's great.
Yeah, so we could go forever.
Yeah.
Because we have lots of questions.
Ah, that is good.
Networks, I have,
Yeah.
so there are some experiences around, but now we have to move to the other building.
Yes,
Things are
that's
going to
good.
function,
Okay.
and we continue there. You mean you say because we have arrangement?
Questions. I mean, this was so super exciting.
Okay, so I go to the other building and I keep contact with,
Yeah.
who's the other person? I have to go to the.
Yes, please. Okay, Laura is going to the other building right now to prepare the other talks, and we're going to have a little discussion here in the meantime. So I'm sorry, I think people on Zoom don't hear that, right? So anyway, we'll see you in a minute. Okay, if anyone has a question, I think should go to this laptop or use their own. You can use your own laptops, right? So to ask a question anyway.
Can I start?
Please.
So,
Yes, please.
okay.
Gerd.
Okay.
Let Gerd go first. Gerd, you have to.
Okay. Now, can you hear me?
This one?
Yeah.
Okay.
Let me know when you can hear me.
It's on.
Okay.
Yes, I can hear you now.
Okay, good. I want to draw your attention to a distinction between what you talked about, out of sample prediction, and what's often called out of population prediction.
Yes.
So it is true that cross-validation is a big progress over just data fitting.
Yes.
And data fitting has been the rule in psychology till about the year 2000. And you find almost no prediction, although it's always called prediction or explained variance. And it's still a rare event in economics, where mostly it's data fitting. For instance, we have looked at the economic papers on satisficing, which is usually optimized satisficing. We have not found a single case where there was a cross-validation being used. But in machine learning, everyone does cross-validation. But there's also a problem with cross-validation nowadays, because you use a sample and divide it up into various things. And the question is whether you can actually predict not out of sample, but out of your population that you have. Yeah? So that means in the future, or that means if you have data about patients in a different hospital.
Yes.
And and here it is, the results can be quite different. But if you have, for instance, in machine learning, if you have neural networks, then you often have, or you can have the situation that the network finds something, say in image recognition, finds something very specific in the sample. For instance, in one study, the neural network learned to differentiate brilliantly between patients at high risk and low risk but it actually found out whether the electrocardiogram was carried around a movable one or a fixed one. And the patients who got the movable one were in the bad condition.
Yeah.
So that you don't detect that in cross-validation,
You wouldn't,
but you see if it doesn't work in the next one. So here it's also I just want to make a point that if you do cross-validation, you still don't know what your results apply to different populations. And it's very important to predict the future.
Yes.
And how can you do that? And that's where simple rules come in, because they are robust, even if you can prove it statistically, because you don't know about the population.
Mm-hmm.
And the case of that Konstantinos mentioned yesterday of Google flu trends, where there's a one reason rule, it's highly stable. If you would take the Google flu data from over 4 years and divide it in 2 parts, so randomly, then you would not find that the simple heuristic performs so well, because you have everything. You miss the changes if something happens. And so out of sample population, out of population prediction, out of sample population, also 2 different things.
Yes.
True prediction is out of population in the unknown future. That's just a comment on.
Oh, it's a very good comment, and I thank you very much for it. I tried to kind of make that point when I said that if you have a model that is just overfitted, then probably the mean is even a better guess. You know, it's a very simple thing. I'll just take the mean and bam, and that's it. And you're perfectly right. Like part of my slides is actually how you can should try to combine explanation and prediction, because if you don't explain your model, if you don't have insight, like especially with like neural networks, there's always the danger of being super overfitted and predicting something that works in your population, but not in another, right? And it can be super dangerous, as we heard yesterday, because these models have an effect. And I remember the case of, I think it was Amazon, where they used neural networks to predict whether people would perform well in their company by just using the applications. And then it worked pretty well, that they actually figured out which persons would perform well in the future. And what it did, it figured out something very specific for Amazon, maybe not, well, unfortunately, not only Amazon, but specific. They figured out that what the model used was male first names. So it just took the male first name because males were more successful, and they used that. And it worked in Amazon because it just worked that way, right? And that is very specific. And it should not, and it could not, well, I hope not to so many other companies, but it should not be used. And this is actually something that is very dangerous if you don't know why your model is predicting something, and it could be super specific to your population. So thank you for that point. That's true.
I unmute myself. Can you guys hear me on Zoom?
Yes.
You have to, so to avoid echo. Can you guys hear me on Zoom? Yes. Okay, good. So I have 2 questions, but let me start with a comment first. Thank you. I am so glad that you didn't have the slides, and so this way it was much more vivid, and I think you explained very well. And even though I understood much of these already before, I still got new insights here. So my questions are, first, you also talked about how to avoid overfitting. And it seems that there are 2 ways now here in the room. The one is you punish those that at some point get worse when it comes to fitting, even though they continue to improve when it comes to training, right?
Exactly.
Okay. So, but this is basically, I would say, a method that determines when to stop. So the stopping point, and this is a famous term in our ABC word.
Okay, yeah.
The stopping point, you determine the stopping point by outcome.
Yes.
Criteria, right? And then what Laura mentioned, this AIC,
the information criteria.
According to my understanding, this is determining the stopping point based on input, based on predictor, namely complexity of the algorithm, number of or pieces of information taken into account. So then we have 2 stopping points here. The one is on predictor variable and the other is on outcome variable. Do I see this right? And how do these two methods or ways of constraining this to stop compare? Which is more successful, and is there also some ecological rationality such that you could say, in these kind of situations, we better make the stopping contingent on outcome, and here it's better contingent on predictor?
Okay.
Can you comment on this?
Yes, that's a very good point. I am not 100% sure in which way Laura meant it, but the stopping, yes, it's exactly as you described it. You would use what I described is do it based on outcome. So, but test sample outcome, right? And I understood it the way that Laura mentioned them. The only way that I could think of to apply them would be also to the test sample. And because they also, I mean, they're kind of dimensionals, right? But they show you deviation from your data, how far your model deviates, but they also include the complexity of your model by the number of parameters that your model has. And this would, I think, have two implications. First, it would work only for a certain class of models that you use in machine learning, because, for example, if you have a regression tree, well, you don't really have any different numbers of parameters for more trees, you just have a different depth of the tree or something. But you could also use it for regressions like, you know, ridge regressions or, well, any polynomial that you want to fit. And also what I would do is I would just include the context, because if the number of variables that you have, like in the context we had yesterday, if you want to give a loan or something, you're working in a bank or in a hospital, the number of input variables is usually rather restricted. If you use something like log data from a smartphone or something, well, then you probably not have to worry about the number of variables. So I guess the economic and social context is what would determine which one to use, and then also which kind of model you use.
Mm-hmm.
How I would see it.
Okay.
Oh, I'm sorry. I thought the first one.
Yeah, I have a second question, but
please.
So my second question is this one here.
I think we have to go over. I'm sorry, but because we're already quite sure, because I think we are waiting for the presentation.
Well, then we can you can ask me on the way. How about that?
Okay.
Yeah.
Habla aquí en este micrófono, habla aquí.
Continue. Things are solved. Please continue with the questions, and whenever you're ready, come over. That's our
All right.
heuristic.
Okay, then,
So guys,
again, thank you very much.
I thought it was an interesting question. Okay, good. So Zoom people, we are now going to the other room. I think this will take something between 5 and 10 minutes before we are all there. And the equipment is already running in this other room, in the other screens from these people, Cesare, and I think it takes another 5 minutes until we start there. So.
Ja. Das habe ich. Darauf wollte ich auch ein bisschen hinaus.
Marita,